All right, everyone. Hello and welcome to Celestial Theodolite update number 18. I'm going to go over a couple of things, and then Mike is going to go over his PDF, and then we'll get into open questions. Okay, so a big thing in what we're dealing with here with the Celestial Theodolite is the physical occlusion versus the apparent occlusion. The occlusion that you see with your oculars, this would be what you're viewing now in this little video here. We have the perspective of it being filmed from the observer point of view, seeing a source of light being occluded by a knife, and then there's a refractive medium between the observer and the light source. And we can see here that when we play out the video, that when the laser is not actually physically behind the physical object there, it doesn't actually occlude. The laser light and the refracted image are still there. They're still present. They're still visible. But at a certain point, when Taylor moves this laser beyond the intersection point of the physical object, it's occluded for the observer with the phone there holding, or, observing it. So that's the significance of what we're referencing here. So there's two reference points to make. We're interested in referencing the angle in which the star was at, or the angle in which the light source was at, in this case, the laser, where it was at when the object was actually occluded. So if we look here, we still see it, we still see it, we still see it. Why is it not playing correctly? Oh, there we go. Oops, there we go. And then it gets occluded there. So what we would do is we're interested in how far behind this knife is it relative to this peak now, because that's what did the occluding, not relative to the observer who saw the apparent light disappear there. So our buddy Goose came up with a nice jig to show this relationship. So here we have some dowels on a platform here, and this is going to be the center dowel here is going to be our occlusion object. This black dowel is our observer. The camera will be placed here. We'll be looking at this dowel and this light source here at the end from this perspective down here. And what you find is when this light source intersects with this dowel right here at about the same one-to-one angle there, because there's not much refraction between these two, that it no longer is visible for the observer down here. So we can put a stick and line up where the light source is when it stopped being occluded versus where the dowel and the physical object are, because these are perfectly in alignment at all times. And then the light source is going to be, that angle is going to change with respect to the refractive medium between the these two things, the physical object and the light source. Okay, so here we have a really small angle, very tiny, right? And then when we add a refractive medium between the two, we find that the light source has to physically be further to occlude for the observer over here, because the light is refracting it over it. It's bendy light, guys. It's the light path length, or the direct line of light there is curved until enough distance has passed to cause a physical intersection between the physical object and the light source, in which it's no longer visible for the dowel observer over here. So when we take off the thing that we had creating the medium there and we line our sticks back up, we see that the angle here has increased. There is a physical difference there. Now, what's going to be put forward for celestial navigation and the globe model and all that is they're going to have uniform celestial refraction corrections to say that the true position of the star is here, but it's being refracted by this much and it's really here. Well, part of what we can do with the celestial theodolite is reference these angles at the time of occlusion, and then we can see how much further, like we could actually substantiate the amount of refraction now. So if they say, hey, we predict 12 arc minutes of refraction, then when we reference the location of the object doing the occlusion and where the star is at, then there should be that same amount of discrepancy before the actual occlusion happened for the observer. So in the case of Pike's Peak, before we add in the numbers here to kind of translate this diagram into the mountain peaks into the celestial theodolite analogy, what we would have here is we have an angle off of the horizon that's what the globe says that this is for this mountain peak is 217. And if you're over here at Nicki Minaj's location, which is 50.7 kilometers away from this mountain peak, they say that the true position of this star is at 2 degrees and 6 arc minutes, but it's being celestially refracted up by 12 arc minutes of refraction, which comes out to be 219 for them. So when this occlusion occurs at Pike's Peak at that time for the apparent position, they're taking this as, okay, the star was down here below this peak by 12 arc minutes. When it was 11 arc minutes, it was still visible. But when it hit that 12th arc minute down here to be 206 as an actual angle, then this star was no longer visible. It goes bye-bye. Nicki Minaj can no longer see it. So that's what they're equating there with this 12 arc. So this pink line here represents 12 arc minutes of refraction. Now, when Nicki Minaj here viewed this occlusion happen, so when the star went bye-bye, and she hopped into stellarium to reference where the star was at with respect to the peak, because remember, we're concerned with the angle on this side to create the occlusion that we saw. This is a cause and effect relationship. The apparent is the effect. The cause would be this physical geometric intersection. So how we're going to determine that is we're going to hop into stellarium and we're going to go to the coordinates of the peak and we're going to say, hey, where was this star's true position at that time? Because the true position would be considered the light source, and the apparent position would be that after image that we're seeing that is delayed because of the motion of the star, the distance between us, and the refraction index between us as well. So what we see is always apparent. What's true is always a mathematical reference to where the star once was at a zenith point on the first point of Aries. So anyway, when we hop into stellarium here and we check to see where the true position of the star was, it turns out it was only 4 arc minutes lower than the peak before it caused a physical occlusion based off of this mathematical reference given by a stellarium, where it would use 15 degrees per hour to predict where a true position of a star is at, and then it'll fill in the refraction difference to say, hey, the star is actually right here, because when you get to lower angles at the horizon, the 15 degree per hour relationship isn't obeyed. The stars linger longer than they're supposed to. So to come up with the difference and maintain usefulness with respect to the system that is dependent on 15 degrees per hour, they say, hey, it's being lifted up this much. So what we've substantiated here is that this relationship of this calculated position only holds if you tell stellarium where you're at so that it can backwards calculate where it needs to put everything. What this geometric occlusion shows with the difference here is that the 12 arc minute of celestial refraction isn't justified as a mechanism of actual refraction. There is some other cause as to why it is lingering that low at the horizon, because if it were actually 12 arc minutes of refraction, then at the peak, this star's true position would have had to have also been 12 arc minutes lower, and it would have matched what the globe predicted for the true position, right, for the observer to cause, if the cause was the effect there, but it wasn't. And the only thing that, like, the big difference here is that 4 arc minutes minus the 12 arc minute prediction there, they're off by 8 arc minutes. So they just invented a completely, that amount of refraction is complete excess, made up entirely to give the optical appearance that the Earth is a globe, and it's obeying the 15 degree per hour, 69 mile per degree relationship for the stars. All right. And then when we add the numbers in here, we can look at this again, show the same thing. So over the 50.7 kilometer distance from Nicki Minaj to the peak, there's a 200 meter drop that converts into 13 arc minutes angularly. You subtract that from what the rise over run to the peak is, which is 231. Subtracting that 13 arc minutes gives you 217. So the physical geometric elevation for the globe is 217. So when we hop into stellarium and we reference where this true position of the star is, if it has any physical relationship to the Earth being a globe, then the true position of the star would either have to be 217 at the time of occlusion or 206 to match their refracted amount to make up the difference. And it's never either of those. All right. So that was my little introduction to refraction and what we're going to be covering a little bit later tonight. And then Mike also has a follow-up to this to go over the relationship of 360 times the distance and 180 times the distance. And what we were touching on last week when they were saying, okay, well, if you do 360 times the difference, the globe predicts 27 arc minutes of drop. And if you add that back and plus refraction, you get the 231. So we're going to go over that exact relationship and see if it actually holds for all observations, because their argument is kind of defining the occlusion mechanism as the only relevant to the apparent. But I've already shown right here with this difference, not met with the difference in occlusions with respect to the refraction amount, to the true position of the mountain peak doesn't, it takes their hypothetical completely off the table that we should just look at it through the lens of the apparent position being occluded. But what Mike's going to show is a further breakdown that relationship doesn't even hold 1-to-1 for every single peak. And if it doesn't hold 1-to-1 for every single peak, then we're not going to consider it as a tenable position. And he's going to show that our position holds for every peak, looking at it in terms of the physical intersection for the occlusion, and then deriving things after the fact for that. But yeah, Mike, whenever you are ready, good sir, we can go over your Prezi.
Okay, I'll go ahead and share my PDF. All right, and it looks like it's sharing. And I won't read this whole thing. I'll kind of summarize it. I've been paying close attention to Jesse and John's arguments over all these weeks, and they've actually been making a great contribution to the celestial theodolite method, whether they realize it or not. 7 months ago, when I first proposed this, I thought plus or minus 2 arc minutes was good enough. But thanks to their criticism, we're actually down to plus or minus 5 arc seconds now, which is the best we'll ever. Yeah, plus or minus 5 arc seconds. And that's the best we can do with 1 second timing. So we'll have to, and one frame per second is the best my telescope can do. So I can't do any better than that without a better telescope. But and just for point of reference, that resolution is comparable to typical mid-range terrestrial theodolites, which cost tens of thousands of dollars. So that's just incredible resolution. And that's all because my GE friends have just this relentless drive for perfection. So, and people who've been here for a few weeks know that our globe Earth friends, their numbers keep changing, and they're using a different refraction all the time. And it may not be obvious to everyone that is necessary, because refraction is influenced by pressure, it's influenced by temperature, and those things are constantly changing. And that's why their numbers are constantly changing. And so Jesse first inspired me to develop the now obsolete J factor, and that allowed me to make globe Earth measurements perfect. And then unexpectedly, when those were perfect, the flat Earth measurements also became perfect. And at the time, I didn't know why. But next, John inspired me to correct the pressure and temperature. And so I got really accurate numbers. I shared this PDF, and it's out in the text. So anybody who's interested in actually getting a copy of the PDF can get all of my data from there. But between Jesse's criticism and John's criticism, we've been able to get this really accurate. And that's when as I was applying this more accurate data, that's when I realized there were minor errors in the GPS coordinates. And so I'm using NOAA coordinates. I've been using those for a while, but when I fixed the GPS coordinates, the NOAA distance changed a little bit. So for the past few weeks, I've been using 50,612 kilometers, but the actual value between my sunroom and the peak is 50,778 meters. And the precise knowledge of that distance allows us to complete the triangle from the observer to the peak. And that lets flat Earth advocates predict an angle of 2 degrees, 30 arc minutes, 36.9 arc 16 arc minutes, and 56.2 arc seconds. So now we have precise distance, precise angles to the peak. And using those very accurate angles, both globe Earth and flat Earth can look that angle up in stellarium using the respective data and um, get within 1 second prediction of when that angle says the peak will occlude the star. Now, for flat Earth advocates, that's really easy. You just adjust the time in any version of stellarium to find out when the elevation of the star is closest to the flat Earth prediction. And you can do this for any mountain, and you do that with atmospheric correction off. Unfortunately, not all versions of stellarium permit changing the atmospheric pressure and temperature, and that's essential to get an accurate prediction of occlusion time if you're trying to do the globe Earth prediction for the observer's location with atmospheric correction turned on. And because of that constraint and the data I'm about to show you, I used Stellarium version 0.22.2 for Linux and Unix to set everything precisely to get very, very accurate indications of when the occlusion would occur. And this graph shows the results of that. Green bars are globe Earth prediction versus the occlusion time. So like for that first star, 39 Aquarii on January 27th, globe Earth was, the globe Earth prediction was 15 seconds behind the observed occlusion. And then our flat Earth prediction was 1 second closer to the observed occlusion at 14 seconds. So basically, this graph is showing you how globe Earth and flat Earth predictions of occlusion times vary across the mountain peak. And you can see that there's no more than a plus or minus 1 second deviation, which is absolutely the best stellarium could do. Oh, and this, by the way, refutes a claim by our globe Earth friends that we're coming up with totally different predictions. We're not. We're essentially coming up with the same predictions. And those predictions are equivalent to each other, even though we're using different angles. That's because flat Earth measures the angle at the peak, globe Earth measures the angle at the observer. And what makes it difficult to see that is the little trick that our globe Earth friends used.
And Mike, can you reshare the screen? I can't see the.
I was about to say, yeah.
Yep, let me unshare. I'm sorry you lost that. Did it disappear when I started scrolling onto the second page? Do you know?
Yeah.
Okay. I'll maybe re-share again when I go to the third page when that occurs.
Okay.
Can you still see it okay?
Yep.
Should see some text, and toward the bottom there's a little piece of a table. And I'll scroll down later and show you the whole table. But everybody who understands the trick that our globe Earth friends are using can bypass the atmospheric correction totally to achieve a perfect equivalence for the two methods. And And basically the trick our globe Earth friends are using is they're rotating predicted flat Earth angle at the peak by the alleged curvature of the Earth to produce an uncorrected globe Earth angle at the observer's location. So at the peak, flat Earth predicts 2 degrees 31 arc minutes. At the observer, globe Earth predicts 2 degrees 3 arc minutes before correction. And under ideal conditions, the refraction correction our globe Earth friends apply is exactly the alleged 13 arc minute, 40.7 arc second half curvature of the globe Earth. And it's only half the curvature. And when they add that correction to the uncorrected angle, they get the 2 degrees 17 arc minutes that a terrestrial theodolite measures and that stellarium predicts is the elevation of that star from the observer's location. So that angle accounts for the alleged d squared over 2r drop at the peak due to the curvature of the globe Earth. And when you added that same 13 degrees 41 arc seconds half curvature to their predicted angle, again, then you're right back to the 2 degrees 31 arc minute flat Earth prediction for the peak without the need for any of their corrections. And then I give you an alternative way to make that same correction. You just subtract the half curvature of the Earth from the flat Earth angle, and then you get a properly corrected globe Earth predicted angle. So these two angles are equivalent. We are measuring exactly the same thing, but our globe Earth friends are taking you through a whole bunch of corrections to hide the fact that all they're really doing is rotating the Earth away from the flat Earth prediction. And then that's what this table shows. This is all of the stars I observed, Pikes Peak occluding, and I give you the date, the time, how many degrees centigrade it was at that time on that day, what the atmospheric pressure was at the observer on that day, the name of the star, the flat Earth angle, the time it was predicted it would be occluded, the globe Earth angle, the time it was predicted it was going to be occluded, and I give you the deviations of each of those angles from the observed occlusion time. So here is all the data I used to generate the graph. And for both the flat Earth and the globe Earth predictions, the amount they deviate from the occlusion time is what I used to call the J factor. And now that's just column GE delta, the globe Earth delta, which is now just the calculated offset from the observed occlusion time rather than an adjustment of any kind. So at the time I first came up with the J factor, I was only hypothesizing why that was needed and what it was. Now we know that's exactly how much the globe Earth prediction deviates from the actual occlusion. And that may result from trees, uneven terrain. There may be other factors. We don't know exactly what causes it yet, but it applies equally to globe Earth measurements and flat Earth measurements. And in this PDF, I give you the exact equation used to calculate the flat Earth and globe Earth measurements. And I want you to note that flat Earth predictions don't need to know the observer's location. They don't need to know the pressure or the temperature. With all of those parameters set correctly, globe Earth predictions match the flat Earth predictions within plus or minus seconds, and that plus or minus 1 second, and that's shown in the last column of the table, which is just the globe Earth difference minus the flat Earth difference. Those being the differences between the prediction and the occlusion time. So I'm hoping you caught what that was saying, that the flat Earth predicts the same occlusion time as globe Earth to within the plus or minus 1 second timing resolution of stellarium. but flat Earth doesn't need to correct for the pressure and temperature at the location of the observer. So I ask you kind of some rhetorical questions here. Why does globe Earth need all of those corrections? Um, and that was not really rhetorical, because I tell you that's the only way they can explain the angles they predict for the alleged curvature of the globe Earth. And so now I ask you another rhetorical question. Why do you suppose flat Earth doesn't need corrections to predict its own and those same globe Earth angles? So at this point, after 18 weeks of discussing this, we've come full circle. The globe Earth shell game is now fully exposed. After proper atmospheric correction, it's clear that the globe Earth angles and the corrections are full and half curvature tilts from the corresponding flat Earth angles. And our globe Earth friends also throw in some terrestrial refraction for good measure. So it's kind of remarkable that they are still trying to claim there's a difference. And you still have the PDF on screen. I've scrolled to a different page.
Yep. We're good.
Okay. So for 7 months now, our globe Earth friends have been refusing to address the fact that the peak indicates the elevation of the star that's predicted by our flat Earth angle, rather than the predicted globe Earth angle. So they have not refuted the null hypothesis that the Earth is flat, and that signifies that the hypothesis the Earth is a globe is incorrect. And this is my original diagram, I think, from 7 months ago, where I showed the flat Earth expectation versus the globe Earth expectation, and the flat Earth expectation is what this method could not measure if it was true that the Earth is a globe, and yet that's what it did measure without knowing where the observer was, and without any kind of corrections, like the kind that our globe Earth friends are constantly applying to their data to try to say that their data is better than ours. Their data needs corrections, ours does not need corrections, and yet they claim their data is better. And one of my flat Earth friends is he keeps thinking he can falsify or refute the method, but clearly he doesn't comprehend the null hypothesis, and he doesn't understand it would have been refuted if the elevation of the occluded star at the peak had been the globe Earth angle, or at least if it weren't the flat Earth angle. But it is the flat Earth angle, and our globe Earth friend, all of our globe Earth friends, seem to be struggling with the fact that the corrected angle from the observer's location is consistent with their predictions, but the uncorrected elevation of the star at the peak confirms the flat Earth prediction. So in other words, all the nonsense from our globe Earth friends is confirmation bias resulting from half curvature tilts in the alleged globe Earth that they misinterpret as refraction, and they need that refraction to confirm their bias. So that's all I have for today.
Awesome. So to be clear, the difference on the J factor that someone was bringing up in the comments there is that you're not using this to correct and calibrate. You're merely noting it this time as it's the difference between the two of like what was actually measured versus what would be expected on the globe.
That's correct. In the GE delta column, that is what used to be called the J factor, because at the time I didn't know where it was coming from. I now know that what the GE delta is the difference between the globe Earth prediction for occlusion time and the actual occlusion time. So what we were doing is just, it was correcting for their error. Now we're not correcting for anything. These are just raw measurements. And the only corrections going on are temperature and pressure corrections so that they can um, they can predict the occlusion time when they reach the angle they predict.
Yeah, are you there, Bull Knight? 'Cause we're typing about it instead of we could just so it's not using it to correct the difference and then make a comparison. It's just showing that this is the difference.
Right. I remember there was originally a J factor that was kind of jokingly called the Jesse factor. That was called the fudge factor. Then
Oh,
there's
yeah.
a whole new J factor, right? And then new
Yeah.
J factor is delta GE.
Well, it's the same thing, but it's not using it as calibration. It's just showing that this is the difference between the two. Because it's the actual measured difference between the predicted time and the occlusion time.
Okay, I think that makes sense.
Yeah.
And just as a little extra, I only discovered that within the last week that that's where the J factor was coming from. At the time I originally came up with the J factor, I noticed, there's this weird systemic error of some kind it looked like, and I didn't know where it was coming from. But if I applied the J factor, it made the globe Earth estimate perfect. And when I did that, unexpectedly, that also made the flat Earth prediction perfect. And I didn't know at the time what was causing that. And I'll scroll back to the graph. Now I know what that's causing that is both globe Earth and flat Earth predictions have a common displacement. And that's the difference between the globe Earth estimate and the observed occlusion time. So that's in the current table, that's called DE delta, and that's what used to be called the J factor before I knew what it was.
Awesome. All right. Well, our guest of the hour are not here, so we can go into open Q&A, I guess. If anyone has any questions, comments about what we went over tonight, I think Beast has been keeping track of the comments. So if there's no auditory comments here, we'll just start reading from some of the stuff from chat.
Yeah, I got only 2 questions.
Fire away.
There was a
champ.
third question, but it wasn't really a question. It was just a picture of Stellarium saying, "What is this?"
Oh,
So
nice.
that was kind of. Oh, there it is, right there. Yeah. So, what is the physical location of the star? Yeah, we can just ignore that. But.
Well, yeah. So for that observer, right, it's not negative under the ground for them. It's out of their field of vision, still above circling. And then for an observer that sees that it's in their hemisphere, it's not a negative coordinate for them. It's not actually under anyone's ground. It's just out of their field of vision. And it's in somebody else's new field of vision. When you look at Stellarium in the way that it gives you this like God's eye view 3D perspective of it, it can be confusing and misleading because you think that you have to like look through the earth to see the star, but you don't have to do that at all. And if you check Shane's Prezi and some of the GIFs that he made, he actually showed the equivalence of the 2 coordinate systems is actually built directly into Stellarium, and you could see it yourself.
Literally shows negative coordinates based on where the location of the observer is and how far away the star is.
Yeah. So physically still above you, but mathematically represented below you. Easy peasy. All right. What was some of the other ones?
First question.
What do you got?
This is from Daza. Would it be feasible to traverse a path, taking occlusion times, and reconstruct the geometry of the surface using CTE or CT?
Yes, does it? It would be all flat. They would connect on the same flat plane that they all measure. That's what we're saying. But that's a great question.
Awesome.
So, yep, it's feasible. All right.
Right?
Question number 2. And I think this is from Ecoplex. How can they, in all caps, possibly think that using stellarium would give them anything other than globe measurements? It's based on the Earth being a globe.
That is a fantastic question. Comes up quite a lot. I'm going to be doing the self promo here. So Saturday, I'm going to be doing a Prezi here on celestial navigation as told to us by the Chinese, and then we're going to go over the Japanese cosmology at the same time because they all had the same cosmology. So we're going to go over the history of that, and we're going to see how they were geocentric flat earthers, because we've all heard, well, you can't be a geocentric flat earther if you're going to be a geocentric, or you have to, that implies the globe, and like all that kind of rhetoric. So we're going to see the exact that the exact opposite is true, and the equivalence of the system that the Chinese were using to cell navigate, and how it's accurate and applicable to now. So we'll cover that in detail on Saturday, and that'll be at 10 p.m. I'll schedule that out. So if you guys want to tune into that, that'll be an awesome one. So in regards to stellarium outputting globe, how could we expect anything different? So like, what is stellarium doing exactly anyway? What is stellarium? What is the globe? Well, the globe is built on the positions of the stars on where they once were on the first point of Aries, which is the night of the vernal equinox in March. So what they did is, for the original stars that they put in the almanac, is they had lads go out and take zenith measurements of those stars on the vernal equinox. That served as their snapshot to define their ground position at a specific point in time, in which they could apply 15 degrees per hour from that from that position. And from there, you could, if you knew your time, you could compare where the star once was, subtract the time, multiply by 15, and get your longitude. So to use their system, they're saying they take these zenith measurements and they call them like the geocentric reference point, and they put this they tie this to the celestial and terrestrial sphere model, where the celestial sphere is a sphere of infinite radius, where they can just make unlimited tangents to stars, from the terrestrial sphere, which is a sphere of a radius of 3959, and they have the two spheres mathematically intersect at that center point at their z-axis. So they place this fictitious observer an observer that just made the zenith measurement of the star on the ground, and they say, okay, suppose we took that measurement of that observer and put him inside of the Earth, and the Earth is a hollow sphere now, and he's in the exact center looking up, making that zenith measurement. So he's in the center of a sphere of 3959, and we're going to use that elevation angle based off of that, because that's how they're relating the celestial and terrestrial sphere model to get that star based on that sphere of infinite radius to relate to a position on the ground to a sphere of 3959 that they're saying. Now, this requires a fictitious observer to tie these points in the sky together. So right off the rip, it's not mutually exclusive to any model anymore, because you're now introducing a fictitious observer. And if you have the freedom to do that, then it's definitely not mutually exclusive. But further, the Chinese had a similar system where they just took the time in which a star transited over the Beijing observatory, and they were doing the same thing when they were out in the wild and they observed that star, and they knew their local time. They would just subtract the difference of where it once was at Beijing, multiply by 15, and they were good to go. And they were all geocentric flat earthers. And like I said, we'll get into that more specifically on Saturday, because that's a whole separate Prezi and whatnot. But the equivalence of what stellarium is and like what it puts out, it's not mutually exclusive to a globe. All it's telling you is where that star is going to be with respect to 15 degrees per hour, and then using different refraction corrections per elevation angle based on where the observer would be observing it at that time. So none of that is mutually exclusive to a globe. They would like us to believe that that is the case, because they went around, took measurements, tying positions of the stars to the ground, but it isn't necessarily the case that it's mutually exclusive in the way that they want it to be. So stellarium is a great tool to do quick calculations to reference where a star is going to be with respect to your local sidereal time. And that's really like the backbone of what it does. I think Shane put in some documents earlier from Stellarium that show the 2 coordinate system transformations it does. It's just doing geocentric to geodetic, which is just referencing the geocentric position, which is that snapshot position of where the star once was to where you're at now with respect to your local time. And it does the local hour angle conversion, which gives you where the star is with respect to Greenwich, which gives you your longitude. So there's nothing in there that is mutually exclusive to a globe, other than the fact that it's using a spherical coordinate system and people want us to think that the Earth is a sphere. That's about it. I missed anything?
Awesome.
All right. Was there one more?
No,
Nice.
that's it.
All right. Well, we were going to do an in-depth discussion with Jesse and or John, but they are not here, and it wouldn't be quite right to discuss without them being here.
Well, anyone else could chime in. You know, anyone,
Well-
literally anyone else who had
Well,
an
don't-
idea. Well, Bacon's here. Hey, Bacon, how you doing? What do you think about this stuff?
Well, the floor is open, but nobody hath chimed.
Bacon's like, I'm
What
cooking
do you think
right
about
now.
what?
I can't.
Well, the celestial
not
theodolite
cooking.
argument. Yeah, you're here.
Oh,
You
nice.
got it.
Yeah. Oh, I have classes in 16 minutes. But
Perfect,
before
it's
that,
enough
yeah,
time.
I'm all
That's
yours.
plenty of time.
Yeah, what do you
That's
wanna
plenty
know?
of time to
I mean-
completely change your cosmology and accept the Earth is flat. Just kidding. Just kidding. It also might not be enough time. I don't know.
Yeah, I don't think so. I've been here for more than 16 minutes and still a glower.
Not convinced yet?
Sorry, I wasn't. I caught the thing on the middle of it, so I had no idea where you guys are now.
No worries, lad.
Well, I can try to make an argument here about the azimuths. I think I tried to do that on text the last time we spoke. I can bring
Nice.
that up again.
Nice. Go ahead.
All right. Okay. So I asked if you think the azimuth to a star is the same as the azimuth to the star's GP. I think you said yes to that.
The azimuth to the star is the same as its GP. Yeah, it should be, right?
Okay. Then, like, how you account for spherical axis between stars' GPs then?
Spherical excess between star GPs.
Okay, let me try to
Well-
clarify. Maybe that was too
So,
straight to the point.
are you talking about like the astrogeodetic deflection that creates that, or what?
No, I'm talking about several degrees of excess. So like you pick 3 points, 3 GPs, and you compute the azimuths between them, and you add them up, you get like 200 degrees or something, depending on how far they are. And you can do it either between the GPs themselves or between
Oh,
the
I
GPs
got
and
you.
the stars above them.
I got you. Well, no. So you're referencing their GPs, which is on the spherical coordinate system. So it should give excess then. Like I don't like it. It
Oh,
is going to be internally consistent. So if you're referencing 3 GPs of stars on a spherical coordinate system, then yeah, it should give it then. That's how I would explain it, that it's an artifact of the coordinate system and not terrestrial topography.
Well, but if the azimuths to the star is the same as the azimuth to those GPs, now you have azimuths between 3 points on the surface of the Earth. On a flat Earth, that would form a triangle. That should not give you excess. Unless the azimuths to the star is not the same as the azimuth to the GPs.
The azimuths aren't exactly 90 degrees. They're like 89.99. They get into different deviations because they don't get exact zenith measurements. And then when they go through and repeat them again, they like average them out. So like, I think you're kind of comparing it against like
I
an
think you're
idealized
misunderstanding me.
calculation. Go ahead.
I think when I say azimuth, I think you're understanding zenith. Like I'm
So-
referring to horizontal
so-
angles.
Right, but to define where
Like
it once
bearings.
was to have its azimuth to begin with, right? They had to take a zenith measurement to start with it. So like I'm saying, like the starting baseline of what they're associating it with to create 3 different positions on their spherical coordinate system doesn't even equal 90 degrees exactly anyway. So like whatever differences they come up with is what I would say is an artifact of the coordinate system and not a physical representation of the ground.
I don't see the connection
Bacon.
between azimuths and 90 degrees.
Bacon, you're familiar with the celestial theodolite, right? Star occlusion times, true positions, angles from a mountain, using stellarium, etc.
Yeah, I understand the setup. I just haven't checked the numbers, but I understand the setup.
Okay.
But that's vertical,
Do
right? That's
you
vertical angles.
do you agree with the setup? Do you see any glaring problems with the setup as a glober?
No, the setup itself, I don't see any issue with setting up.
Really?
Yeah.
Nice. All right. So you make an observation of a star being included by the mountain. You write down the time. You refer to the nautical almanac to see when that true position is, or stellarium to see where that true position is from the mountain. And then you see whether your prediction for globe Earth or flat Earth is closer to that true timing, right?
I would see when the elevation of the star should match the elevation of the mountain from the observer's position.
Well, when we're
That's how
doing
I predict
mutually
the time.
exclusive, yeah, when we do two different predictions, the globe Earth would be lower, have a smaller triangle because of curve, right?
The smaller triangle? What do you mean?
Well,
Which
I mean, it
triangle?
would be a smaller angle, so it have a because you have to subtract a certain amount of height from the flat Earth triangle for it to be geometrically a globe. And the Pikes Peak example, it's like 50.7, or what's the new adjusted number? The super
Yeah, the if you
57.78 meters, right? Which is something like 201 meters a drop over that distance. So your triangle would be 201 meters lower than ours.
the triangle, you mean the triangle between the observer, the top of the mountain, and the base of the mountain? What triangle exactly?
Well, so the triangle we're constructing is based on just the geometry of our observation. We're trying to do a triangle to see the elevation of the star from the mountain, right? So we construct the horizontal baseline. We do arctan rise over run. We get the elevation of the mountain. And for you, the elevation is 201 meters lower. And that's where we get our differing predictions, so that we say our true position would obviously on a globe occur 201 meters-ish below it, right?
Well, to me, it doesn't make sense for you to try to get the angle at the mountain.
Well,
I
that's
don't see how
because
that's helping the prediction.
it's not an optic angle. We're not observing it. We're calculating the true position from the mountain.
For what? How does that help the prediction?
Well, again, we're using arctan rise over run, and when we compare that angle from the mountain in stellarium, we get a result that's very close to our arctan of rise over run and very far from the globe equivalent, which would be a smaller triangle, right? Or anything resulting in 201 meters below.
I wouldn't be building a triangle for the globe prediction. I'm not sure why you're putting a triangle on the globe prediction here.
Well, our starting point was we did arctan rise over run for the flat Earth, and then we subtracted the geometric height in degrees, minutes, and seconds already converted. And when at 201 meters, you convert that to like I think it was 17 arc minutes or something like that. We would subtract that to get the globe prediction. You can do it either way, but now the prediction is that they would do a triangle, and they would use a smaller triangle with an adjusted delta height, or the geometric globe drop subtracted from the flat Earth height. That's how they're doing it now. So if you wouldn't use a triangle, how would you get the predicted angle from the star to the star from the mountain?
Keeping in mind that we're getting our
to the star
triangle
from the
from the
mountain?
observer's position to the peak and the height of the mountain. That's what's forming our triangle. Keeping that in mind, the peak of the mountain, height of the mountain, and the distance of the observer forms a triangle.
Right, that's not a triangle on a globe Earth, right? That's also a geometric triangle. The occlusion time is going to be the apparent, when the apparent position of those two things align.
That's been the problem for the globe Earth, is that the disparity in the elevation for the mountain is exactly what they predict that the drop would be.
As I said, I haven't checked the
Look at
numbers.
the data.
Yeah, I will look at it. That's one of the things I want to look at.
Nice. Yeah.
But yeah, gotta find some time first.
Awesome. Well, if you have any questions or need help with like the most updated spreadsheets, etc., just reach out to Shane or me or whoever.
Yeah, I want to prepare my way of predicting it first, and then I'll take a look at the data and plug into what I'm doing and see if my results match, and
Sure.
then compare them to yours.
Going in
That's usually how I
blind.
do
I like
things.
it.
Yep, looking forward to that.
Yeah, that's how I did the CellNav thing. I didn't look into manuals or anything like that. I just did my own thing and started working, and then I compared to how people do it, and it was matching. So that's how I like to do things.
Good on you, Bacon.
Nice. That's the best way, or that's the way that I learn best as well.
Yeah. Okay. So he has 7 minutes to spare on azimuths, I guess.
I mean, my answer is that it's just an artifact of the coordinate system. Like, I don't.
Okay. If I pick 3 points on the Earth's surface and connect them, that forms a triangle, right?
Yep, I'm with you.
Okay. So the angles on those triangles would be the azimuths between the 2
On the
points
spherical
in.
triangles, right? Spherical triangles
I'm
from the
hearing
sky,
you.
man.
I'm hearing you on a spherical
talking about
coordinate
on
system.
Flutter.
But it's
No,
but it's
on real life.
but in real life, right? It's in reference to a spherical coordinate system that's over the ground. So when you computate it, it's going to be like, oh look, there's excess here, but it's not. And so it's an artifact of the use of the coordinate system, which is my position. So like we don't have to waste 7 minutes on it.
Okay, well, I mean, I see 2 different ideas here. One is that when we compute the azimuths, that doesn't match reality. And the other scenario is when we compute the azimuths, it does match reality. And if it does match reality, then we can use the compute azimuths as real values because it does match reality. Which
Well,
one it is? Does it match reality or does it not match reality? Like azimuths from Stellarium, does that match reality or not?
it's internally consistent with the coordinate system of which it's used. So if you're using it to substantiate where a star is going to be, yes. If you're going to use it to substantiate where the star is with a ground position, yes. If you're calculating,
is it consistent to reality?
Yes, and if you're calculating a triangle based off of that coordinate system, it's going to have excess to it because it's a spherical triangle on a spherical coordinate system. It does not mean that the ground is curved. There's zenith measurements to stars, my dude.
No, azimuths.
Created from zenith measurements to the stars.
If they match reality, then it doesn't matter.
And our position is that the sky is curved through optics, not the ground. So any excess would be due to the coordinate system in which it was mapped from. That's it.
Yeah, but if the azimuth to the stars matches the azimuth to their GP, then that's no longer an angle only on the sky. That's also an angle on the ground because it's the same angle.
As defined by what coordinate system that it was used in?
No coordinate system. We can measure this. This is not in reference to any coordinate system. Like if let's say I see 2 stars, I see Sirius and Betelgeuse. So I grab my theodolite, I point to Sirius, then I move it to Betelgeuse, and I take the azimuthal angle it took me to go from one to the other one. That's not a coordinate system, anything. That's just a measurement between 2 points and what's the azimuth between them. If that azimuth matches the azimuth to their GP, then that's an azimuth on the ground. So that should equal 180 degrees.
No, an arc to arc, because you're comparing a point in the celestial, right, which is then mapped to the graticule. So you get your 1-for-1 relationship between points in the sky and the ground position, and then you're saying, oh look, the sky is curved, so therefore the model we made of the sky is also curved in the exact same way. That's literally 1-for-1 geographic to celestial. Yeah.
That's not my argument. My argument is if the azimuth to the star is the same as the azimuth to its GP, then we can measure a GP between positions on the ground. So we're no longer using angles to the sky because it's the same as the angles on the ground. As long as the star is in the same as azimuth as its GP, then it doesn't matter if you're measuring directly to the GP or to the star. It should be the same.
To the ground position, right? To the model. The GP is how you make the model. That's how you reference the celestial to the geographic. You wait for the time it crosses over that one point, and then relative to that time, that's how you get the ground position. So you're saying from the celestial to the geographic proves that the Earth is curving underneath you. No, it proves that the models are 1-for-1 interrelated and correlative, right? That's what it proves.
I don't see how that changes what I said. Like if we have
Well, it
azimuths
doesn't. I'm
between points on
agreeing
the
with what
ground.
you said. Yeah, I just don't think that it proves that the Earth is curving. I think that it means that the model is one for one reference to the sky, which is what we start with. So then it would
Yeah,
give a
but
true azimuth. The azimuth would match the spherical shape of the model with which it started, right? We're just saying that's not the surface of the curving Earth.
yeah, if the measured azimuths didn't match the predicted measurement, the predicted azimuths, like if stellarium didn't match reality, then maybe you would have a point. But if they do, then you don't have a point because those are just the values of reality. They're not a product of a coordinate system. They are things we can measure directly. So I don't see how.
Stellarium is literally a part of the coordinate system. It does coordinate system transfers, geodetic to local alt-az. That's what runs it. But also we're using we agree with stellarium angles, right? That's where we're using as our corroborative measure. We're saying, hey, in stellarium from the mountain to the star, the true position given by this tool matches the prediction for arctan rise of a run. That's hinging in our argument. That's like, it's pivotal that we agree with stellarium.
Right. So if you agree with stellarium, it no longer matters how stellarium draws its prediction. If you agree with stellarium, you agree that the measurement is stellarium says we get is the measurement we get in reality. So it no longer matters that this is a product of a coordinate system or anything because those are things we can objectively measure in real life. That's no longer anything related to
Well,
coordinate
no,
system. It's
the
something we can directly
observation
measure.
is just of a hemisphere, right? Like this GIF right here in chat, it's of a hemisphere. Whether it's a globe Earth curving at that rate or a flat Earth with limited vision, we observe them exactly the same. So your conclusion and premise is like it's based off this equivalence of everyone sees in a hemisphere. And that's what it comes down to when you're measuring a hemisphere in the sky and you make a model based on completing that hemisphere into a spherical one. Then yeah, you get a 1-for-1 correlation, which is literally how they do geographic to celestial. Yeah, conclusion is our premise, I think.
Well, I wish I had more time to continue on this, but there are 30 students waiting for me, so see you
later, G.
Oh, is it Professor
some other
Bacon?
time.
Professor
Nice.
Bake,
Yep,
bro.
instructor actually. Yep.
Oh, instructor Bacon.
Nice.
Oh, they don't know
Okay,
me as
that-
Bacon, but anyway.
Right. Well,
Anyway,
I assume
gotta go.
Bacon would assert your real name or whatever. Later,
Anyway,
Bacon.
Well, I kind of like the idea of them calling him Instructor Bacon.
Everyone knows what I meant.
If the fact that you don't go by that now is kind of, I'm disinterested in what you're teaching. All right, lads, any other questions or comments? If not, we will go ahead and call it a night.
I have a. Sorry, what's going
Oh, you're coming in super low, John.
Oh, sorry. Oh, there
That's
we go.
okay.
There.
Oh.
I have a question. Yeah. I think Shane and Alan. I don't know about Mike.
What's the question, bud?
Got this earlier. I sent the diagram that I put. I'll put it again in the chat.
You mind lowering it just a tad bit?
Oh,
actually?
okay. Sorry. Oh,
Yeah.
yeah. Sorry. I see that. There we go.
You're good.
How's that? That's good.
That's better. Yeah.
Yeah. Anyway, so I put this. I sent this diagram. There's this constant problem. Jesse asked a question too. If he's not here, I could ask it on behalf of him. I put his question up there a little bit. Where was that? Up a few minutes ago. 551. If you look at 551, I don't know how Jesse will get here to ask it, but it's a question I've asked before too. The fact that the geometric direction to the star from the peak is in a completely different direction than it is from Heffron's place. Is that you shouldn't have to go to the peak if the Earth's flat, the geometric direction to the star is the same at Heffron's place as it is from the top of the peak, but it isn't. Stellarium is very clear about that. It differs by exactly the number of minutes that there are nautical miles between Heffron's place and Pike's Peak, and that's not an accident. That's because the Earth is a sphere. But I just wonder what your explanation for that difference is. Why is it?
I'm so
that
glad
those are
that
different.
I'm so glad that you asked that, John, because I actually went over this last week and your response was, that's a cool bunch of words. So we're going to go over it in great detail.
Good.
Ready?
I'm going to put the diagram up again, and I'll put my version of it as well. So there's the diagram that Jesse drove. So just a second, let me get mine up there as well so that you can address them both the same. It's the same question. But this is the one that I talk about all the time. It comes
Okay.
in the form of that longer
All right.
thing there. So go ahead.
Okay. All right, John. We got Nicki Minaj here on the bottom right. Okay. She sees this mountain peak over here. Actually, let's use this one so it's just a single one. 1 second here. Let me move this out of the way here. She sees this mountain peak, right? Now, it's Pike's Peak. It's true elevation, right? Based on all the flat Earth statistics, right? The distance and the raw elevation difference between her and the actual peak gives an angle of 2 degrees, 31 arc minutes based off of that relative physical elevation of the peak, as if there's no drop over distance, right? John?
I don't understand your diagram. My diagram's much
John.
clearer.
John, this isn't rhetoric time. This is answer
Okay.
simple
Well,
questions.
I don't understand your diagram. Maybe somebody else does.
Nicki Minaj is 50.7 kilometers away. Okay. The mountain elevation is like 22, 27 meters high. That rise over run creates an angle of 2 degrees, 31 arc minutes, right?
Well, it does if the Earth's flat, but the Earth isn't flat. So, I mean, I agree with you. If the Earth were flat, the geometric direction to the peak would be 2 degrees, 31 arc minutes.
Fantastic.
And
Stop.
Yeah.
That's it. That's all we need.
Okay.
Yes, the rise over run to the peak, right? Now,
Yep.
Nicki Minaj, however, right? She's not using the calculated position right now. She's actually using a theodolite. She's got her theody out. And she's measuring now, same distance, same mountain peak, but the angle that she's coming up with is 219.
I didn't
What?
say anything about 219.
I don't give a shit what you said. Are you following what I'm saying?
Talking about that. You're not
Listen.
addressing my question.
We're getting there, buddy. We're getting there. And we're going to follow this to completion. So that way you can't say that's a cool bunch of words. We're going to understand the whole argument to completion. So she gets her theody out. She starts measuring 218, 219, right?
How does she do that?
How does she do
I don't
that?
understand that.
How does she do
I
that?
don't
Well,
understand.
I got you. I'm going to explain it. There's a missing 200 meter drop over distance that converts to 13 arc minutes angularly. So if you subtract that 13 arc minutes from the original 231 prediction, you get 219.
Okay.
I'm sorry, you get 217. You get 217, and then with terrestrial refraction, you would get 219. So this is where this is all coming from, right? So this is why she's saying, hey, I don't know what shape the Earth is, but I'm measuring this with a theodolite as if it's lower in 200 elevations to the tune of 13 arc seconds.
Minutes. Yeah.
Right. Oh, sorry. Thank you. Yes. Arc minutes. Okay. Now, she gets into Stellarium from her location, and it says, hey, this star, 39 Aquarii, right? No mountain peak here. This is just where it's telling her this is at, right? It's saying, hey, I'm actually with no refraction on, I'm at, relative to you, I'm at 2 degrees, 6 arc minutes, but I'm being celestially refracted by 12 arc minutes. So there's a drop over distance between you and the star that equals the same amount as the drop, essentially, just 1 arc minute off. So it's being lifted up by this full amount here. So that's the celestial refraction amount to move the star from 206 to be at, what is it, 217, 219 for the angle, for the apparent occlusion. Would you agree with that based on your diagram there? Right? With me so far?
See the occlusion at 2.
Fantastic. Dude, that's awesome. You see how we started from a position and you were like, where are you going with this? What is this? What is that? But you see how it's starting to come. Yeah. Hey, buddy, we're getting there, but you see how this is, we're not deviating too far from what you're saying, right? We're getting it back there. So now we know where the star is at with its celestial refraction for the apparent position, which they say is the 219 numbers, right? And now we have this mountain peak here, this optical mountain peak with our terrestrial theodolite, right? And we're like, oh, look, it got occluded right here with 12 arc minutes of refraction. This pink line here represents 12 arc minutes of refraction. So
So that's on the other side from Nikki. That's going down the other way. I don't understand that.
yeah,
What's
yeah. So
that all
so
about?
so this is just to kind of represent how this is lower in the horizon to the peak.
Well, it's
So
not
like,
about being lower. The star is high in the sky. It's up at an angle of 2.5 from Nikki, and it's light years and light years away. So it's way above the peak.
John, it's meant to represent the distance for the physical occlusion to occur, right?
Well, the
I
physical occlusion
listen,
occurs
listen,
on the way
listen. As
down,
the star,
is coming down.
exactly, as the star gets further away in the horizon, it gets lower, right? This is what this is representing. The star is getting lower in the horizon. I'm telling you. I'm telling you, this is representing the star getting lower in the horizon. This is the yellow star is the apparent star that you see, and it's following the true position, which is noted here in white with the Aries symbol. So as the true position gets further away horizontally, right, maintaining the same thing optically though, it's following that curve. So as it gets further away, what's the angular separation in angle in terms of where this peak is versus where the true position is? That's how we can determine how much refraction there actually was. So does that make sense so far?
No, not
okay.
I don't have any
I got
idea
you.
what you're
I got
talking
you.
about.
No worries. Let me try again. Okay. So we have this. Let me move this over here. Move this out of the way. Okay. So as you correctly pointed out, right, the stars are always above us, but they're receding into the horizon, either due to Earth curve because we're tilted, we're rotating away from them to create this setting effect. So this is all this represents, right? The stars, still above, right? But it's the way that this occlusion difference is just magnified to show the difference. Go ahead.
Here's the thing I don't really understand in what you're talking about. The ray from the physical star is always headed downward. It never heads upward.
If it's your argument that it never heads downward, then I'm sorry, if it never heads upward, then it would have been occluded way sooner.
No, look at the diagram that I'm basing my question on here. Okay, just look at that thing in the live stream, that text.
John, it requires it to be lifted up to linger in the horizon, bro. So,
my diagram shows how that happens.
So listen, that's great.
Can I just explain what's going
and
on?
exactly analogously to how that happens, same mechanism applies. This is just my diagram of showing the exact same thing. As that star.
Can I just have like 2-3 minutes to explain my diagram?
No, John, because you've explained it and I'm trying to help you understand mine because we're explaining the exact same thing and you're trying to revert back to your thing.
Okay. Can I look? I'm begging you to give me 2 minutes.
You've had all the time. I got your diagram. You went over it. I've seen it.
No, I didn't. I didn't even I didn't say a word about it. I was talking about Jesse's question, which you haven't even addressed. You've been kind of addressing things related to my diagram, but that wasn't what the question that I asked. Now I would like to spend 2 minutes describing my diagram. 2 minutes.
And again, denied. So you can ask again for 2 more minutes. Okay. And I'm just going to say no. Goodbye.
I'm glad everybody heard that. I just
want
to point out.
Nobody cares.
This they did.
Nobody cares.
Yes, they did. So, in his diagram, that's representing the same thing. The star has to be lifted up, right? If we're rotating away at 15 degrees per hour, the star has to follow that 15 degrees per hour, but it stays up in the horizon. That's what celestial refraction is doing. It's lifting it up. So the representation of this is just to show what they're doing mathematically. That's it. He's pretending not to get it, not to understand it, because what happens is this star actually gets occluded with a 4 arc minute difference, not a 12-minute difference, which completely invalidates their whole argument based on using 360 times the distance to use 27 arc minutes to move the observer back to make up the nautical mile difference, all that shit. None of that is even tenable. The occlusion only happens with respect to the physical geometric peak, which isn't represented by the 12 arc minute difference of celestial refraction. It's represented by 4 arc minutes of difference in position.
Yeah, they like to compare apples to oranges now and pretend that they're not, which is why this meme here I put in
So-
is people comparing apples to and not oranges with apples written on it, because then they pretend that it's an apple still. It's really weird.
We went through all of that, and then he starts fucking acting like he doesn't get it, wants to go over his thing again. It's very simple. It's the same thing. It's the exact same thing. Now, this is where the argument ends, because everything that follows after this, because this pink line isn't the same length as this pink line, anything that follows after that's it's false. It's not tenable. So they have a calculated. Go ahead, what were you saying?
Did he actually say the star's not there? It's millions of light years away.
Yes.
God, what kind of exercise is that?
Who knows, dude? Because you can treat it as 6,210 miles away on the Desmo thing, and it does the exact same thing as if it's light years. Like, none of that is relevant at all. The explanation of what celestial refraction is doing, it's lifting it up. Like, it's not making it go. It's not celestial refracting it down. That's preposterous, dude. So, any hoodle. That is the actual crux of it. This is what needs to be actually addressed, because if the celestial refraction amount difference was actually 12 arc minutes, then their position would at least be tenable of saying that, okay, well, the star had to actually optically set down here, because you know what that would mean? That would mean that the star had to that the true position at the peak would have had to be 206 as well for it to visually occlude there, but that didn't happen, right? Because that's not how it doesn't refract 1-to-1 like that. When we went over at the beginning here, the refraction difference isn't 1-to-1 in the way that they want all of that lift to be. Right? That physical intersection shows that. We're separating cause and effect here. The apparent would be the cause, but the actual physical intersection was with respect to that higher mountain peak and when the star intersected here at that 4 arc minute difference. So that is the actual argument. Going through and doing what how about this optical thing if I don't address your position and then maintain mine? That's over, dude. We can't keep doing that forever.
John can, though. He's like the Energizer Bunny. He'll go on for months and just say it.
He will, but I'm not, because this is very simple to understand, right? They're saying that there's this much refraction. We could test that with occlusions, because if this much refraction exists in the way that they want us to think that things are lifted up 1-to-1 to the exact amount, then this right here, with respect to the star, with respect to the peak, should occlude with this longer refraction amount, but it doesn't. It's a third of their prediction. And that goes on for every peak like that. They never once have a peak where the refraction matches the actual occlusion.
Real quick.
What's up?
Shane, do you have that picture of that source code that you posted from Stellarium, or like where that's from, or what version?
No. Nope. I don't know whose comments they are. Obviously, they're not. The source code itself isn't commented like that, right?
Oh,
The question is, are the comments describing the function inaccurate or not?
So I'm trying to find out. If Hammer Eyes can hear me, yeah, show me what you found, because all I can find is the forum pages for it, and then it doesn't really explain it.
I see. Yeah, John didn't like the visual of the diagram, but looking at his, it's the exact same representation. He just has it coming in from higher and then being lower, but refracted up. So, yeah, it's literally the exact same thing. And in that diagram, there should be a 12 arc minute difference between the true position and the peak, not a 4-minute one. So it didn't change the argument at all.
So what exactly is the point of contention, if any? I didn't hear any.
Kind of semantical, because the way that it looks on mine, it shows the star dropping below the peak, and that's not what happens, like, geometrically. That's just an optical thing. But to like make it visually easy to understand the angular difference between the two, that's how I had it modeled. And his shows it kind of more parallel to it coming in at the side, which is like they're both representing the same thing, and there's still that, like, the difference between the two is still like he still has too much refraction. There's still an 8-minute difference. So it was just kind of semantic and then like feet dragging.
Yeah, unfortunate. So you have like the measurement, right? And then you have the data, and then you have the interpretation. So at what point is there any contention so far? Because so far it just seems to be, from an outside point of view, it just seems to be petty squabbling. Not to be mean to anybody, but it's just like, well, I don't necessarily agree with the way you depicted this, or I don't necessarily, well, someone says you're straw manning stuff, but I don't, if they have a different method, why don't they just propose that different method and see if it works differently? If there's different results.
In regards to the using the apparent position thing, yeah, so that doesn't even work 100% of the time. That's what Mike's graph was showing. That only applies on certain peaks, whereas our method is always consistent.
Right, so a different method is just like, it's basically an appeal to possibility, right? So this sometimes gives different results, sometimes it's not. What you'd want the most consistent method.
Right.
Right, so I know I'm asking you to steel man nonsense, but I'm just trying to figure out the point of contention, because the idea that you have some type of rebuttal or refutation would be good. Somewhere. I don't know.
I mean, it's a precarious situation because it's so simple. The star is either going to have to be intersected at a lower angle or a higher angle. Like, there's no, like, that's it. It's like, yeah, there's going to be some slight differences because refraction does affect things, but it's not, but using peaks where the angular difference between the two is significant enough to tell the difference, then it's clear every time. When it gets low, it gets ambiguous, right? Where it could go either way, but the globe's never directly better than flat Earth, unless you do like an individual comparison or whatever.
That Nikki is occluding stars. He did say Nikki a few times, so he was steel manning who was occluding stars, which is good.
Nice. All right, well, we will go ahead and wrap up then. If there's nothing else.
Quick one, sorry.
What do you got,
I was
Dazzy?
muted before. My mic was muted and I was speaking. I thought you were ignoring me. So just a quick question about the Stellarium stuff, the code.
Mm-hmm.
So Shane, what was the implications of the code snippet that you were posting allegedly?
That they're doing geocentric to geodetic transformations. So that's just referencing, where the star once was on the first point of Aries, and then comparing it to where you're at now using your local time.
Yeah. So have you seen the sections of code where they translate all of the other coordinate systems into that common one before they do that? So
Nope.
they have like all of the J2000 coordinate systems, VSOP 87 ephemeris coordinate systems, all of these other coordinate systems for all of the objects that they render. One of the first steps to do in the rendering pass is to translate all of those coordinate systems to a common array declination system, and then
Mm-hmm.
independently. So
Mm-hmm.
multiple coordinate systems in Stellarium, dozens actually. I think there's 11 or 12.
And all of them capitulating to the geocentric reference point?
No, only for rendering. So most of them, many of them are. Sorry, I'm having a mental blank. Barycentric. Some of them are based on other inertial references. That
Depends on what mode, right?
Well, the barycentric.
I'm just looking.
Hold on a
not at
second.
all, no.
Yeah. So the barycentric though is like there's no observer on the sun or like within the or next to the where the barycenter would be, just off center, the center of it or whatever. They don't even have radio stuff there to take measurements of that. It's calculated based off of viewing the sun from our position on Earth. But the actual point, right? Like the actual thing that matters, right, is that for celestial navigation to actually you do the thing that, quote unquote, proves the globe, all of that is in reference to geocentric to geodetic, which is all we actually care about. All the supplemental things after the fact that are derived and added onto the geocentric stuff and also backwards compatible with it. Because if it's barycenter compatible, you could also just convert it back to geocentric. It has to be backwards compatible, otherwise relativity wouldn't be true. So like I'm not like the fact that there's multiple coordinate systems that it doesn't matter at all. So they're all going to be compatible with the original coordinate system that actually matters, that drives the whole thing, that determines latitude and longitude. So like, we're all on the same page.
System, though, it's a geometric model. So they have the VSOP 87 geometric model for the solar system. They have the Hipparchus geometric model for the stars.
Yeah.
Distances and proper motion. And so all of these things are a geometric model. They transform the geometry to the geometry of an observer on Earth and then render the geometry.
Yeah. So did you know that they all share a common z-axis for symmetrical transformations, and that's not really like it? And I don't. And also, when you get in, hang on a second, dude, you're in the middle of talking over me as I'm like talking, man. But listen, I don't care that there's more coordinate system transformations. They're all compatible with the one that's the primary thing that would be assumed to prove the globe. So the fact that there's other ones that are included, that's cool.
But it's not just coordinate transformations; it's geometry transformations as well.
Oh, dude, no way! With a common shared z-axis for the coordinate system to do it, dude. That's great. That's great.
Which z-axis are you talking about?
It would have to be at the center of something. Otherwise, you can't do a geometric or mathematical transformation.
Which z-axis are we discussing here?
Whichever z-axis is in the coordinate system, my dude.
Which coordinate system?
Any of them.
They all have different z-axes.
And if they're not symmetrically aligned, then they're not going to be transformable, dude. The whole point of doing a transformation is having two geometrically aligned axes. So whenever you're going to take two, you're going to take wherever this one's z-axis is, wherever the other one's is, you're going to merge them together. You're going to do your transforms. That's it.
No, in coordinate transformations, you can have any arbitrary axis.
Hold on a second. Nope. We're going to look at a whole book of transforms real quick before we end out, but go ahead and continue. Join my stream.
So a good example is, say we take the GPS ECF coordinate. I'm not going to go into GPS conversation, don't worry. The GPS ECF coordinate system there, right? The z-axis for that is the rotation axis of the Earth, right? So it comes out of the North Pole and the South Pole. That's their z-axis. The VSOP 87 z-axis is the plane, the ecliptical plane, and they aren't aligned. Similarly, in Stellarium, it'll be creating a local z-axis that's vertical, and all of those axes are not parallel with each other. They don't have a common origin, but using coordinate transformations, you can move a point in space between any of those coordinate systems, despite the fact that their axes aren't aligned and may not even be rectangular axis sets.
Yeah. Listen, that's great, but in order for it to work with the geocentric coordinate system, they all have to be aligned in a symmetrical way. Here's a field theory handbook on coordinate system transformations and geometry. And what we find here is that in every scenario, all coordinate systems, as Shane says, we live in coordinate system simultaneity because you can use any intersecting z-axis of said coordinate system to do a transformation and get the relative geometry of the new coordinate system. And they're all equally valid at the same time, given the proper coordinate system transformation rules, which are noted here on the side of each one of these shapes. And in addition to that, you'll notice that every single time here, the common denominator is the z-axis alignment. It's the first rule in the book that they talk about. So I'm going to go ahead, if you want to get the final word or whatever, that's my closing thought.
The axes of orientations are arbitrary. It's straightforward.
Awesome. All right, lads, we'll catch you guys on Tuesday for Ether Cosmology Roundtable number 99, I think it is. That's going to be a good one. And then Friday, we'll do Twitter Community Night. And Sunday will be Globebusters, where I think it's Shane's turn to present on the celestial and terrestrial sphere. So we'll be going over that. See you guys on tomorrow. Oh, and also Saturday. I'll be back on EA Saturday at 10 p.m. Eastern to do a presentation on Chinese and Japanese cosmography, since they are very interrelated and the two prezzies aren't very long. So I'll combine them all into a singular prezzi.